Oh, sorry. Okay, then we can start the meeting. Yeah. Let's see if Janice or others will join later. Um, so, Federico, you had an item today about standard library and BLAS and LAPAC and the work that you do, I guess, in the serving front. The floor is yours if you want.
Yes, thank you, Jeremy. It's a nice introduction, and by the way, thank you all, for being here. This is work that has started more or less a month and a half ago, and so I think it needs direction and inputs from all of you guys. So I would very much appreciate if during this meeting, but also afterwards, if you have comments and ideas. I think it's very important that we come up with something that works for everybody. So the original project basically was posted last year, last summer, and the idea was, okay, we want to introduce in standard lib, some capabilities that are close to, those high-level APIs that we're used to when we use NumPy or SciPy, those, high-level math packages that, basically everybody is accustomed to nowadays. And, ironically, there is no single implementation of such an API in Fortran that people can just download and use. So the idea there was, okay, we want to provide standard lib with this capability. At the same time, the backend for this stuff is as usual, BLAS and LAPAC or LAPAC, I don't know, whatever you want to call it. Which means that basically nowadays every computer's got their own. Every platform's got their own specialized implementation. So we want to provide the user via standard lib the option to use these libraries either as a local implementation if you don't have anything else, or of course if you have a better faster GPU enabled whatever implementation to just link to the external library. So today I would like to show you this couple of things. The work that I've started to do to basically enable BLAS and LAPAC to be integrated into standard lib or into at least into Fortran Lang as a separate package. This is also another thing that we should be discussing, I think. And partner number two, I would like to show you the implementation that I started of the high-level API. So basically, solve, the determinant of a matrix, the inverse, that stuff. This has just started. There's not a lot of functions that I have implemented already. But what I would like you, to give me feedback on is if you think, that the interface is good enough. Like, for example, there is some people that like more the functional interface, others like, overloaded operators or versus, subroutines. People want expert control. Like, I want the program to stop. No, I want to return an error. So I want to show you how I set up this thing, for these few functions that I implemented so far. And if we think that this more or less works as an approach that, maybe down the road, we don't have to change it that much, then I can continue. Otherwise, I think it's the right time to, discuss this. And, an idea would be, for example, to open issues on GitHub or on the Fortran discourse. By the way, I think, after this call, I would like to maybe open a thread on discourse because I think, right now the implementation is large enough that, people could actually start, testing it and, giving me feedback on. Okay, so if you guys don't have questions, maybe can I share my screen? I think it would be better so I can show you, what this works like. So please share me. I think
Should be able, no?
Can I share the whole screen? Window, okay, here. Can everybody see my screen right now?
No.
No. Okay, I'm gonna try that again. Share screen. Allow to share screen. Oh, okay, there we go. There we go. Can you see that now? Not yet, I guess. Let me try again. All right. There we go. Now you can see the screen, right?
Yes.
Okay, awesome. Okay, great. So I'm going to start from the GitHub page because I basically, this is going to be a large project. So I started it as a separate repo just, for the convenience of like, doing a lot of pull requests and, keep the work going a little bit faster. And but, right now I would like to focus on, the implementation. Later we can discuss, what we would like it to be integrated with the standard lib, in what way we want it to be integrated with standard lib. So right now what I have is basically this serves both as the high-level API and as a sort of a meta package for BLAS and LAPACK. It's structured as a Fortran package manager package. So there is an fpm.toml that defines, basically, the usual stuff. The way it works is it uses CPP to basically decide whether we want to use an external library or the internal implementation. The internal implementation is based on the reference LAPACK 3.10 that contains both BLAS and LAPACK. And the way it works, I'm not going to dig into the details, but there's basically a huge script that I started building that starts from the Fortran 77 source code, downloads it, and packages it into modern Fortran. So you will see something like this at the end. For example, let me pick the double precision version. It's actually, I think, total. I don't know. Maybe it's a huge code. So all of the functions have been basically modularized. Is this large enough? So this is just the public interface. Then you will see. Okay, so let me just switch to the code editor. That's probably easier to read. Okay, let's pick, for example, the double precision version. Okay, so there is a public interface. All the functions they've been fully modernized. So if I pick any of them, you will see that the Fortran 77 version has been basically read in, refactored, removed all the comments. All of the constants parameters have been typed now. So all of the variables have, their own integer, real, and complex kind. And they've been standardized. So we have 32, 64, and 128-bit versions for all of the functions. Plus, it's been parsing the intents from the documentation, because the LAPACK subroutines don't have intents, but the documentation has them. Of course, there were quite a few errors in that, but I just read them from the documentation, put them in the subroutine. So all of the interfaces are fully basically modernized. All the parameters have been removed and replaced by calls to the internal routines. So in particular, the license wanted us to rename all the routines. So I renamed everything to standard lib underscore, whatever there was. So that now, whenever we use the reference implementation, it will use the whole package from the local implementation. Plus, all of these things are now basically modularized, so hopefully it could be doing some more inlining than the actual than the reference package does. But I'm not sure. I don't expect huge speedups because, as I said, this is not a platform specific implementation. All of the intrinsics have been replaced. So all of the calls to integer, real, complex, that they were kind dependent, like double or d-complex or whatever, they've been replaced with the kind-based implementation. So all of the calls to int in the library now have their own kind. Same thing for real and all other kind-dependent functions like let me see if I have something with complex, for example. That's probably easier to look at. Let me see here. So anyways, the whole package has been, basically fully modernized. A lot of go-tos have been removed. Of course, I couldn't do 100% of them, with a simple script. So when the do loop, for example, was just like, some random go-tos, I wasn't able to replace them automatically. But most of the loops, such as you see here, they've been, the do continues have been replaced. And this is now just like a very simple modern loop. And in cases there is some follow control like cycle whatever, I retained the label of the original loop. Like, this was, I don't know, loop 170, and there was a nested loop 180. So I retained the label of the loop so that, it still works, in the same way. But of course, you need to be, calling this flow control from inside. So you had to have a label. The label is just the same as before, but it's just now a modern version, and so forth. So this works for both versions. So now what was the cool part of this work? That after I generated the single and the double precision versions from the reference lab pack, everything had been generalized, including the constants. So for example, all of the scaling constants in the algorithms, they are now kind independent. So they're expressed, all of them, in terms of the machine intrinsics that modern Fortran has. So by taking this, I could basically just copy the double precision versions into quadruple precision ones. So that now we can also provide, and I think it's the first time that I see that we have both BLAS and the lab pack for the quadruple precision version. Both real and complex, we got all of the subroutines. So now, long story short, what does the interface looks like? As I said, I wanted to have sort of a preprocessor-based implementation. If you have ideas how to do this better, please let me know. I think this was the best that I could figure out, but I think there may be other options, and in this case, let's discuss. So basically, there is pre-processing directives that I named external lab pack and external BLAS. So in the basically type independent interface, if we define that the user want to use the external lab pack implementation, then we just provide the interface to the external subroutine. And this is copied from the script. So we have all of the information about the intents and everything. So hopefully it's the best we can do for the interface. Otherwise, just use the module procedure. So use the local implementation. This is, of course, doesn't happen at runtime. It happens on build. And in the same interface, we collect all the versions for all the different kinds and sometimes types. So sometimes we have both complex and real versions. I think this is one of those cases. So we have both the real and the complex versions all in the same interface. So this is done for all of LabPack. So there is a big module named the LabPack that contains all of the interfaces. So basically, for every subroutine, the interface, we drop the first letter, and we have the interface with everything else, with the 6 versions per, or depending on 6 or 3 versions per subroutine. This is done for all of LabPack and also all of BLAS that you see here. So I think this is basically, this work is basically finished. Of course, there will be some polishing, some, more debugging, documentation, this sort of stuff. But the nice thing is that we can now provide this to the user in a relatively easy way, I think. And, maybe the standardly built process is easier, but in FPM, you have to still do some work because, of course, FPM doesn't support, pre-processing very well yet. So, for example, I have, the package. Okay, I have some tests now. Later we can discuss whether these tests are useful. But just wanted to show you how the different build process works. So, I can define the macros in the command line interface, but also in fpm.toml, for example. So I want to define, external BLAS and external LabPack, for example, because I'm on Mac, so I can use framework accelerate, right? So I clean up the build folder. Then I can say, okay, I want to run test, for example. I already enabled the preprocessor. Now I need to add to link to the external library. So that would be, I think, flag minus framework accelerate. I think they should work. So we'll take a moment, of course, because these files are pretty large. But like you see here, there is no external dependencies. Like, for example, I've looked in the source code of NumPy, SciPy. They basically do the same thing, but they do it in C. So they package this huge C conversion of BLAS and LabPack. And in this way, we are basically doing the same, but I think we have both greater flexibility because it's very easy to switch between the internal code and the external implementation. And also, I think we have more options here because I think it's the first time that I see both BLAS and LAPACK provided in quad precision version. I think that might be a selling point because people want to use Fortran if it has more options that what they're already used to in Python packages, for example. And I think if we provide the quad precision version, is probably a plus for us because I don't know, might be useful. If someone is working on numerical methods, you want to draw the coefficients for some Runge-Kutta integrator. You need the quadruple precision. So in this way, you can do that very easily. So hopefully when this is finalized, we will have the option to select between the internal implementation or the external library without changing anything. Okay, just, please, the output is still pretty ugly, so please, don't worry about it. But, I understand that it might look pretty bad. So these are the tests. Let's just pick up this number, for example. I'm not sure if that's the slowest one. There are several tests. The matrix inversion, of course, this includes the quadruple precision, and that is not part of the external library. So that would probably take most of the CPU time. So let's say, okay, 0.8 seconds for this test. Now I will try to build this again, but I build it with the internal implementation. So I dropped this macros, and I build that again without the external library. As you see, there is no changes. It's just like changing CPP macros changes the whole build, but the external interface doesn't really change that much because the final point where this act is in the BLAS and LAPACK interface. If I pick, for example, the matrix solve routines, these are also generated with a script because, of course, we want to support several kinds, real and complex versions, and we don't want to write all the code by hand. We want to use a script. So I've been using FYPP for this, but all of the different versions call the interface. So there is no need to specify any additional flags here. The interface is agnostic to whether you're using external library or not. Let's see if compiler has finished. Not yet. So now I will show you how this compiles, and then I will show you the second part, which is the high-level interfaces that I would like to discuss with you. And if you have questions, please go ahead with them. Even if the compilation is in progress.
I think someone put just a question in the chat. I don't know.
Okay, let me see.
How can I find it?
Half precision could be a selling point as it's used a lot in machine learning. Yes. However, I'm not aware of compilers that support Real 16 yet. But I'm not excluding that it would be possible if, whenever that is widely available, why not? I mean, okay, so you're saying NV Fortran does support half precision. Okay, that's a big point. Yes, so let's see if that is possible. So I have a couple of comments. For the quadruple precision version, I had to add some routines by hand because there are some mixed precision algorithms in the double precision version. So they use 64 global accuracy, but they use part 32-bit arithmetics inside, and these involve conversion functions between 32 and 64 bits that they have thresholds. So I had to add those functions manually, basically, but it's limited effort. But I don't see why it wouldn't be possible to basically make it to downgrade instead of double to quad to do that single to half precision. I don't see why that should be a problem. Of course, it will require some work, but everything has been fully generalized. But yeah, very good question. Thank you, Jose. Actually, I think ideally it would be even better to, instead of maintaining, three different versions of these source files, 32, 64, and 128 bits, because they come from the reference LAPACK that does have these different versions. Maybe you could even try to have only one, just, fully kind agnostic version that, inside of it keeps track of the two, the current precision and the lower precision flags could be fully generalized.
Yeah, it was my yeah, I had a question related to that. If you compare the single and double precision, and if the code was the same, if the code is the same, then we could do as in standard library where we have the FIPP preprocessor that loop across all possible kinds.
Right, right. So I think, this is super cool. To do that in practice, it would still require a lot of work.
Yeah, sure, sure.
Because, for example, if you compare, I don't know, LAPACK, the quadruple precision version is taken from the double precision one. So if you compare them, you will see that there are, uses Q instead of D, for example. That's not a big deal, and uses QP instead of DP for the precision. So all that the script does is to replace DP with QP in all of the constants, all of the functions everywhere. Like here, for example, you see that all the constants have been renamed to make sure that the precision is maintained. There is nothing left. All real number conversions, they all have the kind attribute. So everything is now fully generalized. Now we should take for example, the quadruple precision version and use that, which is the most accurate, the most generalized, to go back to double and single precision. So basically to keep only this one. I think that would be very, very nice. Although there is work and testing involved. So let's keep it as a to-do item down the road. But I think it's a very, very nice idea.
Federico.
Yeah.
So in that case, something that I've done before is to add in my subroutines like an integer parameter WP. So I define the precision with WP, and then the header it's also how to say there with WP as how to say as an
Yeah,
argument.
you mean here I could define something like integer parameter?
No, so more like in the subroutine that way. So the implementation you could write it in an include file that
I see.
contains also all the arguments except for the very first. And the very first will be in the subroutine that has the specific name.
Well,
So
I
you will
think
have.
this would be the way that FYPP can do, because with FYPP we could just replace, for example, the initial ladder with the preprocessor macro, say.
Yeah.
So we could have only one, and
if you let me share my screen, I will show you.
Yeah, please.
FPP.
Please go ahead.
If I can find.
Do I have to?
Does it? Do you see my screen? I'm not sure what you see.
Yeah.
Yeah. Don't know if it's large enough. You try to.
All right. No, it's good. Good. Very clear.
Okay. So that's a simple function to compute I think means of arrays, and in this case it's based on the FYPP, and then this is just one code, but it will generate this subroutine for all reals and all complex kinds are stored in this tuple. And then you see that the name will be updated with the kind, the variables also. Here, this is a different kind for real in that case. So that's really easy to do like this, I think.
So the proposal I was thinking, and actually I got inspired from stdlib to do the same thing. But you can take this one step further And so the implementation, you do not use the macros from FYPP. You just only define, let's say, one.wp, and then you just use FYPP to produce the subroutines with correct naming and the kind.
Yeah.
And there's just this WP parameter to change. And that way you just have one implementation file to maintain the include and FYPP to generate basically the interfaces.
Jose, let me ask you a question.
Mm-hmm.
So, so if you do so, you will have 4 different versions, with different subroutine names, in different modules. So, say, for example, in define, after FYPP has, creating the F90 files.
Mm-hmm.
So you will have 4 different modules, for example. The names of each function inside will all be the same, but they will all refer to WP as the working precision. But in the header, working precision changes, and that's fine. But what that means is inside each of these modules, you will have to write the public interface with the generic name and basically duplicate that for each of those modules, because otherwise you cannot use the same function name from different modules, unless you do some additional work to rename names, and I think would be probably a little bit messier. So probably a good idea would be to also rename the functions, not only the working precisions.
So wait, because I think we were doing basically the same thing. So the names you have here will be different within the module. Then you have an interface that generalizes. Then within the module you have the specific names that FYPP can generate.
I see.
And each subroutine internally defines in a parameter to WP, such that the implementation comes from an include.
I understand.
I did that.
You could get one step closer without even having to do the include trick. It's just a strategy to allow you not to have to litter the implementation with FYPP macros. It's just have a parameter that is WP and use it consistently, and then if that implementation doesn't include any FYPP macros, you can put it in a separate file and use an include statement.
Mm-hmm. Yeah. Also works.
It's just a little bit of reorganization.
Stop to share.
Yeah, I think both ideas make a lot of sense. So I think down the road, it's definitely something to do. I think right now the focus was more actually we had a priority on the APIs because there were some deadlines that we had to match. So the idea was okay, but we also need a blast and unpack interface by the same time. So let's try to make as much as possible to make it work. But I think I like this idea of basically trying to merge because it's basically 3 complex and 3 real kinds. Most of the functions cannot be maybe for some of the blasts you can, but for most of the LAPACK, the complex versions have some changes with respect to the real ones. So there is no easy way you can just say, okay, I only have one version for both real and complex, but that's no big deal. I think it's as long as you can simplify at least the kind dependency and make it a unique piece of source code. I think that's a very good accomplishment. Did you have any questions about the way to interface with external libraries? For example, one thing that I left always points to the local implementation is the quadruple precision, because I think there is no way we can. There is no external libraries that provide that. Actually, I think also Apple maybe provides part of the LAPACK only in single precision. I would have to double check the documentation. But anyways, that's not a big deal. But unfortunately, what we cannot do easily is to create a subset of the function that we want to access from the external interface. So we either access the whole pack or none of it. But I think, this is something we can live with.
As you start to get into trying to deal with implementations that do or don't support the whole standard interface, you're going to have to deal with this complexity. And then at that point, it becomes almost trivial to expose that to the user of, hey, which pieces of this would you like to use the external implementation or the reference implementation?
Right. And I think, there is another side of the coin to this. And that is, thus far, what I've been doing is, I have this huge script. So every time it basically uses, it links to the original GitHub report, downloads the files. So it, in other words, it always starts from the clean implementation. And ideally, if there is an update to the reference lab pack, hopefully maybe 70 or 80% of that script will still work. So with some work, maybe we can adapt it to other versions, but still be able to basically upgrade our own internal implementation with that approach. But if we deviate too much from that, I think it will be harder to keep sync with the reference lab pack implementation, which is not a problem to me, because I think, as of 2024 is code that is, so much battle tested that, it's unlikely to have huge flaws. And so I think, to me, it's okay to say, okay, we are going to start developing our own standardly based version that will start, branching out of the original implementation. No big deal. We maintain the license, the references to the authors, and all that stuff in place. And I think no big deal on that side. But we might lose the ability to, in an automated way, download the original sources and process them. I think in the long term is probably not something we want to keep maintaining anyways. Okay, so if you don't have other questions, let me please, share the screen again, because I would like to show you one more thing. Let me see if I can share the screen again. Can you guys see my screen right now? I think, the windows disappeared here. I don't know why.
Yeah.
Okay, so let me now go back to, I think I had the GitHub page here. I've put together, this is pretty fresh, so I don't expect it to be super well written, but this is sort of a summary of the current API. Solve, list squares, determinant, inverse, I, diagonal, and so forth. It's of course a limited subset of functions, but it's just started, so it's still very simple. What I would like to basically have your feedback upon is whether you think that the way the implementation works is both sustainable in the long term, and if you think that's gonna satisfy your use cases, your code style, and all this, details that people may have different opinions upon. So I've been using NumPy, SciPy, and IMSL as basically the reference implementations for the API. So you'll find it's very similar. But if you have ideas, I would be very happy to kind of also, go the extra mile. If there is some additional ideas, I don't think it's a problem to have one more interface. For example, if some people likes a subroutine versus a function, why not provide them? I think, at the end of the day, it's just an interface. So it's something that, is relatively easy to implement. So I want to show you, for example, very quick how I do this. I don't have it here. Let me open. So basically, the way I do that is with FYPP. Let me pick solve, for example, because I think that solve is both valid for real and complex versions. This is the test. Let me see the implementation. I have solve, for example. Okay, there we go. So this is the implementation of solve that I'm using. Like you see here, I'm still, using FYPP. It's not exactly the standard lib version. So when we merge, I will make sure that, all the names and variables are the same as those in standard lib. There is a unique interface, and we basically strip through all ranks, but also all kinds and types means both real and complex. So the implementation is a little bit clogged with this, FYPP preprocessor directives, but it's very useful because, I only implement one subroutine, basically, and we have all of the, if we look at the final compiled version, which is this, we have basically the 12 versions, automatically created. So it's very useful, I think. And the way it works is not via includes, but just, changing the real and the complex. We should have complex versions and the complex, kinds and types, everywhere. Of course, I keep adhering to the style where we have kind in all the intrinsics so that, we are sure that, we don't do any conversions in a way that is not that is not planned. And then we should start the discussion whether, the coding style works. And I think, there are two important things. The first is error control that we should discuss. Do you think the way that I'm coding it will work as a final implementation, or do you have ideas on it? And the second is the options, but that, I think we can also do later in terms of issues. So I try to have this rule, and I think it's very easy to see in the solve version. So we have a very simple interface, but we have optional arguments. The optional arguments are very similar to what NumPy, SciPy have. So for example, for solve, you just specify, okay, solve AB, and the result is X. This is functional style, so X is the result of a function. We always have allocatables, so we can we need to keep track that for example, even in case of error, we need to return something that's allocated. But the way error control works is we use optional output arguments. So I define this linear algebra state type that I will show you later how it's made. It's a derived type that stores information about the error. So if you want that as output, the code will never stop. So maybe it might return an error message. For example, in this case, I'm providing a matrix with the wrong size. I have the return object on output, so it will return the error state, but will not stop the code. But if you don't request an optional output, so you just run solve AB, for example, and something goes wrong, the code will stop. The way it's implemented is, there is some very limited flow control. So for example, here, something happens that doesn't work. Okay, so generate an error state, which has information about the routine that it happened upon, an error flag, and some messages that describe what the error is about. Then you go to the flow control routine, error handling, that I will show you how it works. So the error handling routine is very simple. Basically, if you don't provide the output argument, it will just stop the program. If you do provide the output argument, it will just return the error state. Okay, there we go. So it's a very simple routine that, there is an internal error variable, of course, that we always create. Then if you want it as output, it always just returns the output object or the output object. But if you don't have it and there is an error, it will just, print that to standard error unit and stop the program with the state flag. That's it. Very, very, I think it should be decently fast. The way I design it is that there is no allocatables inside. So hopefully the compiler should, be able to handle its memory as quick as possible. There is an error message that is up to 512 characters and the subroutine length up to 32. I think we can change this later if they're suboptimal. Message length is maybe too long, it could be 256 or 128. But I think the idea for not using the string type in this case is that a lot of people want linear algebra to be as fast as possible. So the idea was, okay, we don't care about using strings in here because we just provide a simple message. So let's just use fixed size character. And then, of course, there are some routines to basically compare this based on the integer flag, but also to set them. The way I set them is here. And for example, if I set that without a location, but I could show you also the one with the location. There's just basically a bunch of optional arguments. Some of them are scalars, some of them are arrays. So for example, if you want to provide, and then there is subroutines that basically convert this into messages. So the scalar message chunk will add for a string, if that's a string, will add, will print an integer if that's an integer of various kinds, will print a real with the precisions that are defined in standard lib if you add a real number. So what you see in output here, for example, these are the style, these are the styles that represent the complex numbers and the real numbers that are defined in standard lib. Now, to show you real quick how this flow control works, I think I made a sample app in the Fortran in the FPM package. This is really stupid, and I apologize about that. But so, for example, I'm using linear algebra. I want to create a diagonal matrix. For example, how does the kind information for the functional style work? Well, I'm using something that is similar to the allocate Fortran keywords. So for example, if you want to have a diagonal matrix and specify the kind, you use mold, and then you specify the type and kind of the object that you want. So in this case, it is a quadruple precision real number. If you specify here something like this, it will create a complex identity matrix of size 10. So in this case, we're just trying that for a real version, so very easy. We create the identity matrix. We allocate some very simple result. That's 2, just to not have all ones, and then you solve. So now if I run this app, we should see, okay, actually maybe I have to save. And if I run this app, then we should see, I think the result is 2 for all variables. And this is quadruple precision numbers, like you see, very many digits out of this. So now let's assume that there are some problems. For example, I'm using a equals 0. Now, as you see here, I'm using the solve interface that doesn't have the error control. So I expect that the code should stop. So if I try to run the application again, what I see is, okay, solve return algebra error, singular matrix. And stop -2 has the error code of the linear algebra error. So the execution will stop if you don't provide the error flag on output, but you want it to run. So if you don't want the code to stop, you just add the error as the last argument. Solve state, and you print. I think this should not stop the code because we requested the error message on output. There is no, I need to specify the name. So if you now run this, the code will not stop, but the error information is stored in the error object. So if I print the context of error, it will say, okay, algebra error singular matrix. It will contain the same basically message, but you just require that on output. So the code will not stop. So in this way, you have both the option to have flow control, have safety. So you don't want your code to stop, then you provide an error message always that will contain information. If everything goes right, for example, I don't have a singular matrix, then it just returns 0 as the error flag. So no solve state success. and the error flags is 0, so you don't need to do anything. Of course, you can check that with this simple logical error. I think error is a Boolean function that tells you whether something wrong was happening. And this is done for all the interfaces. So I, for example, contains interfaces for both creating the identity matrix, but also diagonal matrices. I don't know, maybe you want a diagonal matrix with the something on the diagonal. So it could be a scalar or an array of values. It will create diagonal matrix. For the matrix inverse, for example, have 3 different interfaces to the same operation, because I found that there were different implementations. So I thought it was cool to have all 3. There is functional interface. Functional interface will return the result of the inverse matrix without destroying the input. Subroutine will destroy the input and overwrite the input matrix, and also the operator interface that some people might like. Same structure, so if you don't provide the error on output, then the code will stop if there's something wrong. And so all the 3 interfaces basically represent 3 different coding styles, because the operator, you cannot have, you can only have 1 or 2 inputs. You cannot have anything else. So you cannot provide the error flag on output. So if you're super sure what you're doing, maybe you can use the operator. If you want to sometimes save some memory, you can use the subroutine version. And otherwise, you can use the functional style. One last thing before I stop talking is the way that I'm using the pointers to do both the functional and the subroutine style. I want to show you, for example, in the solve interface. So what happens, some people might want A to be destroyed, and some people might not want A to be destroyed. So of course, we have to declare that in-out intent. But so the user might want it to be overwritten to maybe save some memory, or have an idea to get some performance gain. So you set overwrite A equal false. So if you don't want it, internally there's a pointer. So pretty conventional approach. If you want to override, so I name this copy variable. So if you are allowed to, if you don't want to copy variable, you just point to the original variable, and that will be destroyed on output, or or updated on output. Otherwise, you just allocate an internal version, an internal copy of it, so that you will always work on the pointer version, and then on returning, if had been allocated, you deallocate that. As easy as that. So the idea is to try to cope with all possible coding styles, but as I said, I think what matters here is people that start using these functions and tell you, okay, this is something I don't like. Maybe we should change this and that, and so forth. So as I said, if you have questions on this stuff, I think probably the best way is to open issues on the repo, because we can have more discussion there. Plus the discourse, of course. Any questions? Let me see, because I don't see you guys. I want to see you.
Yeah. A couple of thoughts, and maybe this is just my style, but I prefer functions to always only have intent in arguments, which generally means that they can be pure. And I think you could probably get as far as doing that with all your subroutines as well, marking them pure, with one subtle change to your error handling. Instead of having an explicit write and a stop statement, you can still generate that string but use error stop, because error stop can appear in pure procedures.
Oh, I see. Okay, this is very interesting. I guess the only limitation this idea has is, how do we double check that all the functions in LabPack are actually pure, or can be made pure? I think probably this is the biggest hurdle, because I think I 100% agree with your idea. And actually initially I thought let's also make them pure, but it turns out it needs probably a lot of changes in the original LabPack, because all the character part is handled pretty much the old way. So
Yeah.
I think ideally it would be fantastic, but probably also a lot of work.
Sure.
But it's nice to hear that. So what you're saying is, if I go back to the state here, well, there is some internal rights, and I don't think they are pure, so they cannot be pure. Probably we would need some pure versions.
Internal rights are pure.
Yeah.
Okay. So this is not a problem. So what you're suggesting is probably I should. No, where is it? No, I don't have error stop. Only have stop. So if I remove the right and I replace the stop with an error stop, then it should be pure.
Correct.
Yeah. You can even
Awesome.
you can even pass your message in it.
No, you can pass your message. Replace
can
your right and stop with error stop error %print.
Yes, it's what I mean.
So I could even print a message out of this.
Yes.
So, and if I do this, what number is passed to the, what exit stat is passed to the operating system?
It is processor dependent, but I've never seen an environment where it was 0.
Okay. Because so I don't know why you should be using it, but the idea for passing the error code to the operating system is, I don't know, for example, if you launch the Fortran program from within another library, for example, you could query that exit code instead of having the results of your calculation passed otherwise.
Right. I mean, I've rarely seen a Fortran code that gave meaning to the exit status, other than 0 means we exited successfully and non-0 means we didn't.
Okay. Okay. So, well, I usually do. So I'm probably the only one on earth, but yeah.
Mm-hmm.
I think it's not strictly necessary in most of the use cases. I agree with this.
And technically, the standard says that it is also processor dependent whether that error code is provided.
Yeah, and I think if you're on Windows, it's probably slightly more flexible. But if you're in Unix, I think it has to have a negative ID, and it has to be 0 to 250 to minus 255, something like this, because Unix uses positive for other stuff. So yeah, I totally agree. It's it's not super portable, but I use it typically in my codes. But as you're saying, I'm probably the only one.
The other thought I had was you're worried about having static sizes for your characters. I tend to not worry about performance in the error condition.
Yeah,
you really want to go fast, but if something went wrong,
you're right.
isn't nearly as important.
Yeah, I guess probably it's just like we're not talking about anything really performance-wise meaningful, but the fact that we always have an error variable in every function. So I thought maybe if you have allocatable components, maybe the compiler will force it to be on the heap or or to be static. I don't know what the compiler might be doing. So I thought maybe the easy way here is to just fix the character lengths and just live with it, because at the end of the day there's never going to be very long messages. You see that here. What you want is like, okay, metric size is wrong. So something not so complicated, singular matrix. There are just a few error messages, and in fact I think it could even be shorter, because 512 characters is probably a couple lines on an average terminal. On nowadays larger screens, so it's probably too much. Maybe we could do 128 and. So I don't know. I think I appreciate your opinion on this. It's probably hard to say, what performance, change. Like you're saying, hopefully it should never happen. It should never reach this line. but yeah, I think let's try to be, what I thought is let's try to be flexible, but at the same time, to put an effort to be as fast as possible. So it was sort of a trade-off between the two.
Yeah. But my point about functions not having intent out or in out arguments is because it really does immediately become undefined behavior, right? So if I want to add, so for your solve example, if I want to say x equals solve of AB plus solve of AB.
Right.
If I didn't say don't overwrite A, it is completely undefined behavior what answer I get. And especially if you end up actually doing any IO. If I want to say print solve of AB, I think I've seen situations where G4Tran likes to deadlock.
Yeah, indeed.
Yeah. It deadlocks all the time when you do IO inside functions. So I understand. I think this is an important point. So I think we can get as close as possible to this, except for the LAPAC interface, which unless we put together a huge effort to kind of go through. I think it's literally 500,000 lines of code. So it's even if you simplify, it's a lot of work.
I'm not saying you need to